The monitoring of individual jobs gives buffer management excellent control by exception over the whole process. The monitoring of individual jobs gives management excellent control by exception over the whole process. That means you only manage by exception. You don't manage everything day in and day out, which is the usual practice. We all have a plan versus actual meeting and every item is looked at every place. You don't need to do that in buffer management. It works for the whole company as well as individually on each processes as well. So how does it work? The whole drum buffer, which is of 90 hours, and this 90 hours applies to all the items in the pipeline. This 90 hours is divided into 3 sections. Here is the buffer for an individual job, which is at the second step of process, as shown in black. In buffer management, however, where the job is located is totally not important. Since we are now tracking everything on time, it doesn't matter where the job is. But visually, it is present at the second stage. So the 90 hours given for this job to be completed is being measured. And the buffer is divided into 3 zones. In each zone, there are 30 hours. These 3 zones are referred to as green, yellow and red zones. So the buffer gets divided into 3. The current buffer status of the job is determined by the time that has elapsed since the job was released. That means I know the start time and how many hours have passed since the job was released in the system. And if that time is less than 30 hours, it is in the green zone. That means it's okay. It's doing fine. However, here is another job at the same stage. A little more time has elapsed since it was released. For this, we are saying that the buffer, the green band of the buffer has been utilized. Now it is in the yellow band, but it's still located at the same place. Which job should you do first? But natural. The job which has consumed most of its buffer time is on priority. You should do that first. By consumption of buffer, we mean that in 90 hours it has to actually be there in front of the buffer. That means is manufacturing time start at the buffer 90 hours from the time it was released. It has already consumed more than 30 hours of its time and still lying at the second stage. Whereas at the second stage there's another job which has consumed less number of time. The priority gets set by seeing the buffer penetration of the jobs. If there is no red zone penetration, then strict first in first out is the perfect tactic. Can you work out why? There are at least 2 reasons. However, if a job has penetrated a red zone, as you can see in the figure, then it has been held up and it now has priority over the other jobs in front of it. FIFO no longer applies for the job. So there's a third job lying at the same place. It should have not been there, but it's lying there. So break all the rules and make sure you chase the job which is penetrated into the red zone and you do it first. FIFO applied as long there was green and yellow. We find that what we find is that most red zone jobs are safely waiting in front of the drum. This is how we design the drum. That any item which is actually into the red zone should be lying in front of the drum. That means it has still a wide range. It could arrive at 60th hour or it could arrive at 85th hour. But somehow all the jobs lying in the red zone should be lying in front of the drum. Some jobs get there earlier. It can happen that some jobs can get there while they are in the yellow band only, and some jobs can get later. It doesn't matter. But any job in the red zone or any job that has penetrated the red zone is a priority job and it has to be chased. By analyzing the buffer status, we know the status of all our jobs all the time. The floor will prioritize a job if it penetrates the red zone, and the management can intervene if the penetration looks as though it will threaten the schedule. By saying that the job has penetrated the red zone, it does not mean the job is late. It says the risk is very high that job will be late. So there is still a lot of time for you to take corrective action. It is not like the usual process where only when something has not been on time you get a report saying that this was not on time. So buffer management is an ability for you as a company to actually take corrective action to manage the lateness of the order. And that really is the essence of drum, buffer, rope and systemic production. We exploit the drum and we subordinate everything else to it. I believe it can't get any simpler than this. You have removed all the complexity out. You are not micromanaging. You're looking at the drum, and your buffer management is telling you which are the orders which have a high probability of getting late and which are the orders doing fine. By moving to time-based approach to managing operations, one is also relieved of the inherent variation in the system which is caused by the unbalanced line as well as the product mix, and making the system simpler is the biggest benefit one gets by using drum, buffer, rope in operations management.
In concepts of flow, we very clearly brought out the fact that if an organization has to be cost effective, it has to make sure that the flow of the products or components through its shop floor flow at a high rate, and increasing this rate of flow is what makes the operations more effective. However, for making sure that the operations were effective, there was one more condition in play. This was a practical mechanism for limiting overproduction. Now, we also said that if the flow or the speed of flow of material through the shop floor was slow, the inventory would pile up, and the flow of material is actually nothing but an alternate way of saying that we have to reduce the lead time for production. Somehow during that discussion one gets a feeling that inventory and flow, or inventory and lead time for production, are related. Hence, it is not a common misnomer or a misconception of people who say that please reduce inventory in the system. Purely focusing at reducing inventory in the system has never led to a reduction in inventory. But just to look at inventory in isolation is what is the problem. If we say that reduction in inventory on the shop floor means increasing of flow, then reduction in inventory makes sense. And for God's sake, please do not say that the aim of the operation is to achieve zero inventory. Zero inventory is associated with a shut shop. If you are working on a component, what is that? That is also an inventory. So the idea is to make sure that we have the least inventory in the system by focusing on increasing flow. How do we test it out? Let me try and explain what I just said in words by using this simulator in front of us. To begin with, let me explain the simulator. Here is basically a display screen which has 4 to 5 elements of information which is required and generated within an organization, a manufacturing organization. At the bottom here is a schedule. Schedule means there is a date, there is a time, quantity, the work center on which the product is being performed, and the operation sequence. Let me explain. Order. That means the order for the shelves is being worked at the work center called machine, and the operation number 1 is being performed by this work center. When we come to the right, we see that it is 15th of August and 80 pieces have been produced. And this is how you read this. The columns with red date means it is an off day or it is Saturday, Sunday. Green means it is today. So this is nothing but the loading or a Gantt chart made after one has scheduled all the operations on the shop floor. What you see here is the number of units present on the shop floor. Hence, this display is called the WIP part. For this schedule, which is playing out on the shop floor, this is the kind of inventory present on the given day. 350 is the highest, so around 300 units of inventory are present on the shop floor. So here is the WIP, here is the manufacturing schedule. Let's go to the left part. The left part, you can say here, is nothing but the demand. So this company, which manufactures shelves, doors and cabinets, has got a demand of 160 unit each, and as I've always mentioned, demand should have a date. All the 3 components are required on the 24th of August. Below this is what we call the machine details. Machines are organized by work centers, and these work centers are controlled by a calendar, and the rate of production of every machine is written here. So if you have to read this, the work center called machine has got an overtime calendar in place, and when it works, it produces 15 units per hour. Here's the demand and here's the machine center. Because it is when we want to manufacture the demand, this demand will be sequenced through my work centers, and these work centers will produce at their rated output, and hence the product is done. Let me go on the top to talk about a bit of policies. Here in the display I have assumed that every date is nothing but 24 hours of production, and my planning policy is push or pull. Let's begin with the scenarios. Let me go and make sure that I have allocated the correct calendar, and let me go and make sure that I am going to start planning from today into the future. My demand says that all the shelves, doors and cabinets are required on the 24th of August, and the quantities are 160 each. The criteria to start planning is shown here. Today is the starting point, and today is the 19th of August at 8 AM, and hence the Gantt chart will display this. Like I showed you earlier, that every machine works to a calendar, and the calendar decides the number of hours available for it to produce. That means depending on the working calendar, the capacity of a machine varies, not the rated output. The rated output remains constant per hour, but if the machine works to a different calendar, the number of hours it has to produce the units will change. Here is a normal calendar. Please look here. Monday, 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 and 2 hours each. This is the most scientific way of laying out a calendar, whereas I just make sure that every row is nothing but a time band in which a certain number of hours can be made available for a machine to work. So here, if the machine starts its operations at 8 AM, finishes at 10 AM, 2 hours have been made available. The next band is at 10:10. That means between the first row and the second row there is a time difference. The end time of band number 1 and the beginning of row number 2, there's a 10-minute difference, which actually means to say that there's a 10-minute break at 10 AM. The second time of operation starts at 10:10 and finishes at 12:10. Then there is a 40-minute break, and then the fourth band of operation starts at 12:50 and finishes at 2:50. Then there is a 10-minute break, and then we again begin at 3 o'clock and finish at 5 o'clock. This is called the normal working calendar, and in normal working calendar we are getting 8 hours of work every day. We also have an overtime calendar. When you look at the overtime calendar, you will see that now we have 10 hours of work. Instead of the schedule finishing at 5 PM, now it is finishing at 7:10 PM.